Welcome, everybody. There are not many people here in the room, but I expect I hope that there are more people in Teams, right? Okay, so today we have here Jacobo Ramos, and he will give an oral presentation around 20 minutes, more or less, okay? With the title, Improving the Performance of Alignment-Based Conformance Check. So please go ahead.
How we improve the performance of alignment-based conformance checking. And in order to speak about conformance checking, I have to first explain what is process mining and what are processes, because conformance checking is one of the areas of process mining. So process is simply a set of tasks or activities. They are organized, they have some structure, and have a clear start and a clear end. Process models are the way that we represent and execute processes, like the one that we see in this picture. This is a process of a subscription renewal service from a hosting provider. And it starts by receiving an expiry notification of a subscription. Then it retrieves in parallel information about the customer with these three activities. And there are the middle section controls the payment. And this payment can be successful, in which case this branch is executed, or it can fail, in which case this branch is executed. If it is successful, several services are extended in parallel as parallel activities, and a notification is sent to the customer. If it is a failure, then a notification is sent to the customer, and the process ends in both cases. So I have to explain now what is process mining and why is it important. Nowadays, systems record a lot of event log data as they are processing more information. So these event logs, these logs contain a lot of information that is very rarely processed. Process mining does this. It helps organizations discover, monitor, and enhance their processes by extracting knowledge from these event logs that I'm talking about. So why is this important? Because real processes often differ from the processes that were originally designed for the business or the organizations. So using real data to back up your claims about your process really helps to take better decisions. So now I will explain what are event logs. The event logs are just a list of events, like the one that we see on the table on the right. And events, each row of the table is an event, and it must have a timestamp, the activity that was performed, and a trace ID. Events are grouped into traces by the trace ID. Each trace is a complete execution of the process model. So, for example, the trace case 234, which is the one highlighted in gray, contains the activities enroll, class, test, and exam. That is the sequence of events that was performed in the trace. So now, how does conformance checking relate to process mining? It is one of the areas, as I said earlier. Process mining is made of process discovery techniques, conformance checking techniques, and process enhancement techniques. Process discovery techniques take as input an event log, and they automatically generate a process model. This is done by identifying the relationships between the activities seen on the log. But as I said earlier, this process model is usually very different from the process that the user expects. So we have to analyze the differences and improve the process models later. So this is why conformance checking techniques were created. They take as input an event log and a process model, and they identify and evaluate the discrepancies between them so that we can find errors and fix them. Then the process enhancement techniques focus on improving the process model based on the insights given by the conformance checking techniques. So now we can move on to explaining the problem that we're trying to solve. But first, we have to explain how we represent and execute process models. We use Petri nets as they are the most used modeling notation for conformance checking. Petri nets are a graph of places and transitions. Places are the circles and transitions are the rectangles. Places can contain tokens, which are the small circles inside of them. And transitions have a label that corresponds to an activity of the event block. So in order to execute a transition, you consume tokens, you remove them from the input places, and you generate tokens in the output places. I will explain this with an example that I will use throughout this presentation, which is a simple virtual course, a very simple process model. This is a process in which the students can enroll into the course. Then they can take any number of classes and tests, and they complete the process by performing a final exam of the course. So to execute the enroll activity, you consume the token from the input on the right-hand side, and you generate the token in the output. Next, you can execute the class or the test transition. Both of them are enabled because they have a token in the input. And when you execute them, one of them, you generate a token in the output. Now, a silent transition is enabled. This behaves like any other transition. It is the black rectangle. It is there to help with the structure of the process model. But if we execute the exam transition right now, we reach the end of the end place of the model. So we complete a process execution. Now, there are different conformance checking techniques. So I will explain why we chose alignment-based conformance checking with an even simpler example. Imagine that we have a model that only accepts the sequence of the activities enroll, test, and exam. And we want to execute the trace enroll exam. We have that trace, and we want to check the conformance of that trace. Where are the errors? What are the discrepancies between them? So we could execute, like I've just shown, the process model, the trace on the process model, but this would give us that the trace is not conformant. This is not enough information. We want to know where the errors are and how conformant it is, because, for example, the exam activity was performed at the end of the trace, and this is correct. So another technique that we can use is token replay, which consists of forcing the execution of the trace on the process model and ignoring all errors. These errors are returned as the diagnostics of conformance checking. In this case, we would receive these results. There was a missing token before exam and a remaining token before test. This has a couple of problems. First, we need an expert to analyze the results as they are tied to the modeling notation. And furthermore, this gives us two errors when the actual error was very simple, which was removing the test activity. So for more complex models, for non-trivial models, this would be confusing to analyze. So alignments were designed to solve all of these problems. An alignment is a sequence of moves that executes all of the events of the trace and executes all of a complete model, performs a complete model execution. The available moves that we can use are a log move, a model move, and synchronous move. A log move executes just the next event of the trace. A model move executes an activity in the model. And asynchronous moves does both things. It executes the same activity in the trace and in the model. So we can see an example of an alignment here. It is the alignment of the activity of the trace enroll exam test and the same model as before. And this alignment has each column of the alignment is a move. The synchronous moves are shown in green, and the asynchronous moves, which are the log and model moves, are shown in yellow. But this definition has a problem, and it is that this first alignment is also a completely valid alignment for the same trace and model. But this alignment is only made of asynchronous moves. This gives us no useful information what we actually want is the alignment with the least amount of asynchronous moves. In order to do this, we define an optimization problem in which we try to minimize the number of asynchronous moves by assigning a cost to them. And what we want is the optimal alignment, the one with the least amount of asynchronous moves. So the advantages of alignments are that they identify the root causes for errors. For the previous example, we can see that the alignment tells us that the test activity shouldn't be performed before exam, should be performed before exam, but it was performed after exam. Those were the errors of the trace. And furthermore, another advantage is that they're independent of the modeling notation. So they don't require an expert to analyze the results. The disadvantage of alignments is that they are very computationally intensive. The state-of-the-art struggles to compute optimal alignments for complex or real process models and logs. So our objective is to improve the performance of optimal alignments. And now we move on to describing our algorithm. It is based on the A-star algorithm, which is an optimal and complete search algorithm. It explores a dynamically built graph to find the alignment of the least cost. This graph contains states which are or nodes which are partially built alignments. These are alignments that start at the beginning of the trace and the model, but do not necessarily reach the end of the trace and the model. So we build this graph by constructing neighboring states from each state. The neighboring states are the ones that add a valid move to the previous state. I will show this with an example now, but first, the A-star algorithm explores states by increasing order of cost plus heuristic, where the heuristic is an underestimate of the remaining cost to a goal node. And that possible valid heuristic is the one that that considers the remaining trace as synchronous moves and computes the cost of this remaining trace as the underestimate of their remaining cost. So now I will show an example. Here we can see the graph that will be built as we explore with the A-star algorithm. And here we can see the current state. The initial state is the only state of the graph at the start, which is an empty partial alignment with no moves. So we select it to explore it, and to explore it, we discover the neighbors of the state. The neighbors are the valid moves from the empty partial alignment. And these moves are a log move, a model move, and a synchronous move that are added to the graph as neighbors. Now we select from the unexplored states the one with the least amount of cost plus heuristic, which in this case is the synchronous move. And the algorithm repeats itself until we reach a goal node, which is a complete alignment. So we discover the neighbors of this node. We select more the states with the least cost plus heuristic, and we discover their neighbors. We continue doing this until we reach the goal node. As you can see, the goal node performs we use the same trace as before, so the optimal alignment is the same that I've shown earlier. We can go over this later because there's not enough time to explain everything now. So we identified some performance issues with this algorithm that we fix in our contributions. First of all, the heuristic is fast to compute, but it has really bad accuracy. So the A-star algorithm cannot benefit from it to accelerate the search. We are exploring states that will not lead to optimal alignments. And the process model rules are checked on every iteration, and this can be slow. So first of all, we proposed a new heuristic. It balances the execution time and the accuracy of the estimates. It works by also using the process model to estimate the cost. A subset of the required transitions that must be executed in order to reach the end of the model are retrieved, In this example, we can see that the enroll transition must be executed to reach the end of the model. And if these transitions do not appear in the remaining trace, we can increase the cost estimate by 1 because there must be an asynchronous move on those required transitions to reach a complete alignment. Now we move on to state reduction techniques, the first of which is SR model. This technique allows us to force a model move under certain conditions. The condition to apply this technique is that the enabled transitions of the model, in this case class and test, do not appear in the remaining activities of the trace. If this is the case, we can skip all other moves that are not model moves because they would lead to an alignment of a cost greater than the alignment of this if we perform these moves. The SR-log optimization is similar, but instead of forcing model moves, it forces log moves. And the condition to apply it is that the next activity of the trace does not appear in any of the alive transitions of the model. The alive transitions of the model are those that the transitions that could be executed at any point in the future. For example, class test, but also exam and the silent transition in this example. The last of the state reduction techniques is a greedy search. It is a very fast depth first search that we perform before the main algorithm. This search works exactly like the A-star algorithm that I just described, but instead of considering all unexplored nodes to select the next node to explore, it only considers the neighbors of the current state. So it always adds new moves to the partial alignment, and it quickly finds a suboptimal alignment. And this suboptimal alignment is used as a threshold or as a limit for the cost plus heuristic of discovered states of the main algorithm. So it can remove even more states from the search. The last of our proposals is faster execution of process models. We do this because the process model is checked for enabled transitions, and all of them are executed in each iteration of the search. So the way that we do this is to convert the Petri net to a simple automaton, but we do this only as needed, dynamically. This automaton shows for a state like this one, it shows the enabled activities as arcs, and the arcs takes the state to a new state, which would be the one that we arrive to if we execute that transition. So it is much faster to execute the transition if we check this automaton than if we check all the rules of the Petri nets. Now we move on to the evaluation. We use 227 log model pairs for our performance evaluation, and we focused on using different logs from different sources, from different domains, and most of them are real, but we also include synthetic logs to increase the complexity and the variety of the samples. For the models, we use manually generated models, but we also discovered ones automatically. Most of them are discovered with different techniques and different complexity parameters. So we use from thousands to millions of log events, and from a few model transitions to hundreds. The first of our checks was an ablation study. It consists of enabling and disabling optimizations selectively in order to check how they improve the performance of the algorithm. So we measure the performance in terms of average number of explored states and the execution time. Our main conclusions were that the optimizations scale well with the complexity of the inputs, the logs and models, and that the optimizations work well together. They increase the performance even more if all of them are applied. Now we move on to the comparison with the state of the art. We used 10 different algorithms from the state of the art. most of which return optimal alignments, but some of them can also return suboptimal alignments. The problem with suboptimal alignments is that you don't know how close they are to the optimal ones. So you don't know how bad their approximations of cost are. This is the main graph of the results. It shows for each of the algorithms a line. This line shows how many log model pairs were computed for optimal alignments in less than the given amount of time in the x-axis. So our algorithm is called REACH. It is the bright green line. And as you can see, all of the algorithms solve the simplest log model pairs in less than a second with similar performances. But REACH quickly rises above the other ones, meaning that in the same amount of time, REACH solves many more log model pairs than the other ones. Now I will show the same graph, but for a limit of 5 seconds instead of just 10 seconds. Here we see that REACH solves 95% of the log model pairs in less than 45 seconds, whereas the other algorithms take much longer, and they still solve, they slowly solve more log model pairs if given more time, but they in 5 minutes they solve less log model pairs than REACH. So we can solve more. We solve more log model pairs than them. The conclusions are that we have presented REACH, an A-star-based high-performance algorithm for computing optimal alignments. Our contributions were a new heuristic that balances execution time and accuracy of the estimates, the several techniques for reduction of states, and an efficient replay of the process models. So we validated it and tested it against 10 algorithms from the state of the art. And we found out in our evaluation that REACH aligns more log model pairs than any tool from the state of the art in less than 45 seconds when the state of the art was given 5 minutes. It is also much faster than the state of the art. For example, in just 10 seconds, it solves 26% more log model pairs than any other tool from the state of the art. Now, for future work, we plan on working on declarative process models. These are a completely different paradigm from procedural process models like Petri nets. They are a list of business rules like the one that we see here. And the main difference with procedural process models is that procedural process models specify explicitly all of the allowed behavior. Everything that steps out of the process model is not allowed. Instead, declarative process models, by default, they allow all of the behavior to happen, and they add rules that must be enforced in order for the process to be complete. This gives us much more flexibility, so the declarative process models are more suitable for flexible environments like hospitals. The alignments are still applicable to declarative process models. As I said earlier, they are independent of the modeling notation, so we can use them with declarative process models. The problem of performance for computing optimal alignments is much worse for declarative process models because the flexibility of the models also means that from any state we can perform many more activities. So there are many more moves to perform, and the graph can be much larger for the search to the graph that will be searched will be much more bigger, larger. So we also intend on working on multi-perspective conformance checking, which also considers data attributes in the process models. This means that we would not be limited to control flow checking. We could also add restrictions on the data stored on the event logs. So are there any questions?
Okay, let's thank the speaker. Okay, so is there any question? I don't know if people through Teams can talk or not. They should. Any? Okay. Yeah. There should be people in Teams, but if there's nobody, people from the audience here can.
The the science on it. But from the point of view of the presentation, I would like to congratulate you, because I think you made a very good presentation. It was quite clear even for people who is not working on this topic. And the quality of the slides and the way you were explaining, I think this was really good. I have to say, at the beginning, I missed maybe a little bit the point. What was the whole point? Why you were doing what you were doing? Might have to do. I missed the first slide, so this might be the reason. But it was also not clear for me at the beginning whether the different methods you were discussing were your own methods, or something that was on the literature. This was also became clear later on when you compare with the state of the art. So one assumed that these methods were, let's say, developed by you, but I think it doesn't hurt to say that from the beginning to avoid misunderstandings. But anyway, I think it was a very good presentation. So congratulations.
Thank you.
Okay, more questions? More questions? Any other questions? No? I have a couple of questions. So the thing is this, at the very beginning, I missed in the title the word process mining, but now I realize that maybe it is not only applicable to process mining, your method for alignment-based conformance checking. Am I right or not? I mean, because at the end, you mentioned that you were to start with a declarative process. Is that process mining too?
Yes, that is also.
Okay. Okay.
Process mining is a very wide area that works with processes and event logs. So there are, as I said, there are process discovery techniques, conformance checking techniques, and process enhancement techniques.
All right.
Focus on conformance checking, and inside of conformance checking, we focus on alignments, alignment-based conformance checking. And these alignment-based conformance check techniques can be applied to any process model. They can be procedural process models, or they can be declarative process models.
All right. Now I see it. Okay, it was a question from the perspective of a person who doesn't know anything about this field. So another question is, on slide 24, you showed some graphs, some plots. And the thing is that I was wondering if this is a genuine, curious question. So what would it happen if we extend, the execution time graph? I mean, would the other methods reach the same performance as yours?
In this graph, we show how for a 5-minute timeout, it's already an extension of the previous graph.
Okay. Yes.
However, I executed this for longer, and around the 8-10 minute mark, we solve 1 or 2 more process models, but the other ones get stuck. But I haven't tested it with more than 10 minutes.
All right. And the question is how important the time is, because you apply this with 2 domains of applications, with 2 references. At least this is what I have seen on your slide. So the time is important, I guess.
Yes, the time is. You don't want to be checking for conformance for hours. You want to get the results right now to be able to analyze them.
So it would be like an online method more than an offline method.
There's also the possibility to apply this to traces as they happen, so you can check and fix them as the errors happen. Yeah.
Okay, and now a more general question, curiosity. So have you published any papers? In what state you are in your thesis?
We are working on it. We are in the revision process of the first paper for these rich algorithms. And we are also starting out to work on the declarative process models.
Okay. Thank you very much for your answer. Any other question? Any other question from people from the other side? No? Okay, so we end here. Let's thank the marvelous talk, the marvelous speaker again.